Welcome to section 5.2, the characteristic equation. We're going to talk about what the characteristic polynomial is and also the characteristic equation for a matrix. We'll use that to find the eigenvalues of the matrix and then understand the definition of similarity. So first of all, we recall that a scalar lambda is an eigenvalue of a matrix A if we have the equation AX equals lambda X has a non-trivial solution. And so we can write the following equation. We can actually look at the determinant. Let's look at why that works. So if we start with our AX equals lambda X and we subtract out that lambda X, and if you remember last time, we kind of snuck in an identity matrix times that lambda, then we're left with the equation A minus lambda I times X equals 0. Well, this has a non-trivial solution if, and really if and only if, that's written with that two F's, the matrix A minus lambda I is not invertible. If it is invertible, then we only have the trivial solution. So we want it to not be invertible. Well, if it's not invertible, then its determinant is 0. So we want our determinant of A minus lambda I to be 0. We can actually use this to find eigenvalues. So if we take the determinant of our matrix minus lambda times the identity, which just looks like lambdas on the main diagonal and zeros elsewhere, well, then what we're really doing is we're taking the determinant of, let's go ahead and subtract this out. We have 3 minus lambda, negative 2, 1 minus 0, and negative 1 minus lambda. And that equals, we multiply sort of like the 2 by 2 crisscross, minus negative 2, and we set that equal to 0. And then we want to solve that for lambda. So we need to multiply this out and we get negative 3 plus lambda minus 3 lambda plus lambda squared plus 2 equals 0. I just FOILed out that equation, and so that leaves us with lambda squared minus 2 lambda minus 1 equals 0. Now sometimes you'll see an obvious way to factor your equation and sometimes you won't. If you don't, you can always use the quadratic equation, and so remember that you have your solution is negative b, so we have a is the coefficient of the first thing, b is the coefficient of the second, and then we have c. So we do negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. And so that's going to end up being 2 plus or minus the square root of 8 over 2. And so our two eigenvalues then for this particular matrix are 1 plus root 2 and 1 minus root 2. I got that by factoring out. Square root of 8 is, just to make sure that you guys are good with this, square root of 8 equals the square root of 4 times 2, which is 2 times the square root of 2. Okay, so that's how we find eigenvalues. Now, sometimes this is hard because if we have something that's a bigger equation, it might be harder to factor or harder to solve. And that's just a fact of life for us, unfortunately. Also, it is okay to have square roots, as we've seen. Section 5.5 deals with what happens when these are complex. We may or may not do that in this particular class, but that would be what happens when you get a negative underneath that square root. Okay, so let's look at some slightly easier characteristic equations. So if you have an upper triangular matrix or a triangular matrix in general, remember that the determinant of b minus lambda, well, that winds up still being the determinant of an upper triangular matrix because even though we subtract, oops, that's not F0, even though we subtract a lambda from the diagonal elements, it didn't change the fact that it's upper triangular. So we wind up with 5 minus lambda, 2 minus lambda, and negative 3 minus lambda. And that has to equal 0 for it to be an equation. And this is how you can remember it has to be an, you always have to set it equal to 0. It's because an equation has to have an equal sign somewhere. Okay, so now our first quiz asks you to compute the characteristic equation of this matrix C, which doesn't quite have, it's not upper triangular because it has that 1 in the lower left. So you're going to need to use maybe the crisscross version. Okay, so we can also talk about something called the algebraic multiplicity of an eigenvalue. So here again we have a matrix that is upper triangular, and even if it's not 3 by 3, any matrix that's upper triangular can in fact you can take its you can take its determinant by simply multiplying down the diagonal. So here's our characteristic equation, and then what we're asking about is the eigenvalues and their multiplicity. Well, the multiplicity is the number of times it appears as a factor. So for example, 3 minus lambda is one of the factors. So 3 minus lambda equals 0. So lambda equals 3 is an eigenvalue, and it appears only once. So its multiplicity is 1. If it appeared 5 times, its multiplicity would be 5. And so for your quiz, you can see that lambda equals 5 is also an eigenvalue. And now I'm asking you what is its multiplicity. So you just need to count how many times it appears. Okay, now if we have a matrix with a given characteristic polynomial, we can use that to find the eigenvalues as long as it's not too nasty. And this one actually factors out nicely. We can factor out a lambda to the 4th, and we get lambda squared minus 4 lambda minus 12 is going to have to equal 0. And so, but let's simplify that a little bit. So this is a situation where for me, I was able to kind of think about how to factor it. Well, just a really quick review. You think about two things that multiply together to get 12, and you want them to add together to get 4. So it's kind of a fun little math thing. So I think of 3 and 4, that makes 12, but it doesn't give me a negative 4. So I'm going to go with 6 and 2 makes 12. I need a sign on it, and since that 4 is also a negative 4, I go with negative 6 and positive 2. And you can double check that actually negative 6 times 2 is negative 12. Negative 6 plus 2 is negative 4. Okay, and we need to set this equal to 0. And so now we have lambda equals 0 is one of our eigenvalues that comes from this guy here. And that lambda to the 4th is like lambda, really what you want to think about that as is lambda minus 0 times lambda minus 0 times lambda minus 0 times lambda minus 0. So that's that eigenvalue 0 showing up 4 times, so it has multiplicity 4. And then the other two are lambda equals 6, because when you plug in 6 minus 6 is 0. And so that only shows up once, so that has multiplicity 1. And lambda equals, now we have to be careful here, this lambda plus 2 equals 0. So that means when we solve for lambda, we get lambda equals negative 2. And that also has multiplicity 1, since it appears 1 time. Okay, and so now we want to talk about the notion of similarity. So if we have two matrices they're said to be similar if one of them equals P times the other one times P inverse for some invertible matrix P. And so we've seen this I've been prepping you for this all along, right? So this is an important concept that will come back to us periodically. And so we want to show that, in fact, if they satisfy this property, they have the same characteristic polynomial. And so to do that, we first can note that if A equals PB, P inverse, well, that actually implies let's multiply by P inverse on both sides. So P inverse A equals P inverse P, B, P inverse. And then these P inverses become the identity. And we can also write, there's a reason for me doing this. I'm also going to multiply on the right-hand side by P. Okay, and so then what we end up with is P inverse AP equals B times the identity, which equals B. So basically it goes both ways. And why do I want to do this? So we have B also equals P inverse AP. So I'm going to use that now. So let's look at B minus lambda times the identity. Well, we can replace B by P inverse AP. So I'm going to plug in P inverse AP for B. And then I'm also going to make a substitution for I. The identity matrix is P inverse times P. So why we're doing this is actually so that we can pull out our P inverse and our P. We'll see in a moment what I mean by that. So, but the first step will now be, and this is one of those proofs that I call hindsight is 20/20 proofs. There is no way I would have thought to do this if I just sat down and stared at this without having seen it before. And so this is certainly not something I would expect you guys to come up with like on your own randomly. But it's a cool proof to kind of go through to see, like it's a very crisp proof in my opinion. It's kind of neat. So first of all, we can pull that lambda inside our parentheses we have a theorem in section 2.1 that says when we multiply by a real number, we can kind of move it around. It's commutativity of scalar times a real number. And then we can further take this and make it, we can factor out that P inverse. This is the associativity property of matrix multiplication. Then we're going to try to factor out that that P, but we need this lambda I again. And so let's go ahead and stick an I in just like we've been doing. And so finally, then we can factor out. So this is just like the reason we could stick that identity is because multiplication by the identity doesn't change anything. And now we're doing the other side of the factoring. And so that is theorem, I believe, 2C from section 2.1. Okay, so now what's nice about this might not look so nice, if you haven't seen this before, but we've got an A minus lambda I and a B minus lambda I. So let's go ahead and see what happens when we take the determinant of both of these sides. So when we take the determinant of the left-hand side, we have to take the determinant of the right-hand side. And then we have rules about determinants that tell us once we have a multiplication happening, we can distribute the determinant. And this is, I believe, section 3.2, theorem, I think, 4. And now the determinant numbers are real numbers. This should remind you of a homework problem. I think maybe it was homework 6 that we did. So when you have real numbers, they commute. And so we can move those determinants around, even though we couldn't move the matrices around when we were just multiplying matrices. So this is because real numbers commute. We have commutativity of real number multiplication. And now we can go back and use that theorem 4 again to stick that P inverse and that P together. And so this is again section 3.2, theorem 4. And that's the identity matrix by the definition of the inverse. So since P inverse P equals the identity, but the identity matrix has determinant 1. It's just a bunch of diagonals. It's a bunch of 1s on the diagonal. And so finally, what we have is the determinant of B minus lambda I equals the determinant of A minus lambda I. But that gives us the characteristic polynomial. So that's exactly what we wanted. Okay. And then, so our last step is we're going to look at actually verifying that these matrices A and B given are similar. And then we will we'll look at what happens with their eigenvalues. So if we want to verify this, we write down P, we write down B. If you want to pause and try to find your inverse of P, you can do that. Here's what it is. And let's go ahead and multiply these things out. So if we do the P times the B, we get 3, -4, 6, -6, and then times that P inverse that you paused and computed. And so that when you do that multiplication out, you will see that you will end up getting A. So A and B are similar. That means they have the same eigenvalues. So once you found the eigenvalues for one, you can find the eigenvalues for the other by simply, they're the same, you don't have to do anything. So let's find an eigenvalue, let's find the eigenvalues for A. So remember we do the determinant of A minus lambda I, and that's basically we subtract lambda from the diagonal entries. And so we wind up getting -1 minus lambda times 6 minus lambda minus -6 times 2 has to equal 0. And when you factor all that out, what you should end up with, and again, you can pause and check your algebra and then jump back in with us. So we have lambda squared minus 5 lambda plus 6 equals 0 when the dust settles, and that gives us lambda minus 3 times lambda minus 2 equals 0. So our eigenvalues are lambda equals 3 and lambda equals 2. Okay, so now here's a question that we're asked. Find a basis for the eigenspace of A for one of the eigenvalues. Let's just pick one randomly. We'll choose lambda equals 3. You can try this for lambda equals 2 as well on your own to just kind of see what happens there. And let's look for a basis for the eigenspace. So we want the eigenspace, and actually I've given you abbreviation for this. So I like to use eigenspace of the matrix A corresponding to eigenvalue 3. So what we do is we're going to subtract that eigenvalue from the main diagonal, and then we'll row reduce that. And when you do your row reduction, you should get 1 -1/2, 0, 0. And so x1 equals 1/2 x2, x2 equals x2. And so a basis for this eigenspace is 1/2 1. Right, so I'm just using that parametric equation, parametric vector equation. So let's look at lambda equals 3 for, let's try to find a basis for the eigenspace of our matrix B. So again, we do the same thing. We do 3 minus 3, 0, 0, and then 2 minus 3. We subtract 3 from the main diagonals, and that gives us 0, 0, -1. We row reduce that. This is one of those weird cases where you have a 0 in the first column. And so we get x2 equals 0, and actually x1 is free. So we can sometimes write that as x1. And so if we wanted to make a vector for this, well, x1 equals itself and x2 equals 0. These are all of our solutions. And so a basis for the eigenspace of B3 is the vector 1, 0. And what you should notice here is that these are not the same, right? We had 1/2 1 for the eigenspace for A corresponding to lambda equals 3, and 1, 0 for the eigenspace for B corresponding to lambda equals 3. So the eigenspaces are not the same, even though the eigenvalues are the same. So that's an important thing to take away.